We are absolutely in the last part of the course, and we are talking about multiple integrals, and for this you need a maturity level which many people in this varied audience might not have. Those who do not have, you may even skip this part without any problem. Those who have some maturity in thinking, they can take a very good look, they can run the lectures repeatedly or even take a look at the books. Lectures are there, but books cannot be replaced, otherwise there would not have been any books and everybody would be just lecturing and giving notes. So, because books are organized, so thoughts are already organized in a book and you can give a proper discussion. For example, we are going to first talk about how to integrate a function f x y over a rectangular domain. So, now we are in say 2 dimensions and I consider a rectangular domain. So, here is my A, here is my B, here is my C and here is my D. So, the rectangular domain D, this one, consists of all x y, where x lies between B and A and y lies between C and D. So, this is my domain and I want to ask the question, what is the meaning of this integral? Can I, if I write a symbol like this, where f x y is a function of x y, so z equal to f x y, and dA is the elemental area, which you can write as dx dy also, dx into dy. You have an elemental area taken out of the given domain D. So, what we do is you basically divide the domain into rectangular grids. So, if you take this one for example, and if you say this part is dx and this part I mark as dy, then this elemental area, this one dA, this is a very small area, okay, the picture it looks a little bigger, does not matter. This is actually dx into dy, it is a rectangular area. So, it is basically we are asking what is the meaning of this integral. Essentially what it means that given any such grid, a grid is just like a partitioning that we have done on Riemann when we studied Riemann integrals. We partitioned the line, here we are partitioning the domain. When we partition the domain, what we do is the following, we construct the following things. So, you take a, say the midpoint of every domain you take as a reference point and then you construct these sums. So, at the kth domain and del ak is the area of the kth domain, basically do it for each and every one of them, then you start making the partition finer, means you are taking the domains with smaller and rectangles of smaller and smaller area. So, if you take the limit of the area Sn as n tends to infinity, when n tends to infinity because that means the number of your partitions, number of your rectangles here becomes very large, as a result of which you have more and more, even each sum is a bigger sum basically, meaning you have more terms in that sum. So, you want to compute this and suppose these are the finite value say L, and then this finite value is assumed now written as is defined to be the integral or double integral of f x y over the elemental area dA. You can also write this as in terms of the limit. In fact, Fubini showed that if f x y was continuous, you can actually sweep the limits, you can change this order of integration. This is only for a rectangular area. For a more general area, you have to do something else. So, this fact is what is called the Fubini's theorem. Now, what does this tell me? What does this double integral tells me? It tells me that just like you find an area under a curve, under a surface f x y, z equal to f x y represents the surface, the graph is a surface. Essentially, when you are integrating over a rectangular zone, you are finding the volume, the solid that can be placed under that particular area. So, this is my domain D, and suppose this is my surface S, then the volume. So, this is my surface that you have, say f x y, z equal to f x y. Now, this surface is a graph of this function f x y, and now this is my domain D, and you are suppose you fill it up with say solid or some solids inside. So, then you are going to find the volume of this region enclosed by the domain D and the planes on the four sides here. So, this integral, if you look at the volume V, this is actually integral D f x y dA. So, let us just go in and try out one such example and at the same time verify the Fubini's theorem. So, suppose you want to calculate the volume under the plane equation of a plane in 3 dimension is given as x plus y plus z plus constant equal to 0. So, this defines a plane. Now, I want to find the volume under the plane. So, what should one do? So, here is this thing, something like this, and the domain that is given to you is the following rectangular region. So, it is up to 2 and that is up to 1, y is up to 1, y axis, x axis, z axis. So, you are basically trying to find the volume. So, there are many ways of looking at it. So, by Fubini's theorem what we can do, you can verify Fubini's theorem. To find the volume, we basically now have to compute the integral, x is from 0 to 2 and y is from 0 to 1, and this is my function 4 minus x minus y dx dy. As a first step, you would just integrate the first integral in terms of x, where you will keep the y constant. So, for what you will get back is a function of y. So, it is 0 to 2 4 minus x minus y dx, and that will give you. So, what will this give you? So, it will give you 4 x minus here I will get x square by 2 and here I will get minus y x, and this has to be put within 0 to 2 dy. So, if I put it within 0 to 2 dy, it is simply going to give me the following function. It is going to give me, if I put 2 here, 8 minus 2 square is 4, 8 minus 4 minus 2y. So, it is 6 minus 2y, right. So, now I have calculated this integral and then I will get this one. So, what I will do now? I will just now have to do this. So, it will become 6y minus y square 0 to 1, and you know that this will give the answer 5. So, you can check it up in the other way also, you can try it in the other way, you can do 0 to 2, 0 to 1, 4 minus x minus y dy dx. So, you first integrate with respect to y holding x constant and you will get a function of x, then integrate with respect to x. You can verify that the answer would again be 5. So, this is a very basic idea which come, and these two are same. So, it also verifies the Fubini's theorem. There is some more general thing in the Fubini's setup is that sometimes you know this y does not vary between a fixed number, it is not a rectangular one. So, y varies between two functional values of x, that is okay. You have x varying between a to b and y varying between the values of two functions g1 and g2 which are continuous. So, g1 and g2 are continuous functions. In that case, how would you really, what is your, so my domain now is this, my rectangular region or the domain is this. So, then in that case, what is the meaning of this integral? How do you compute it? So, it will be, because now x is fixed, keep that as the outer one, do the functional calculations, because y is in now terms of functions of x. So, you have to put y as the inner calculation, that I integrate over y first and then x. So, you can do this. It could be also different, meaning R could also be, for example, if I have a region R, say R hat, where y is given, the region of y is fixed, but my x is varying between two functional values of y given by two functions which are continuous. This result is also due to Fubini, and this Fubini was an Italian mathematician, he gave these results in 1907. It is a very pretty old game as you see. So, now your y should come outside, because that is the outer variable which is fixed, and now this would remain, because ultimately you have to get a function of y to integrate over y, and here I integrate over x first and then y. So, this is what will happen if I take a, but sometimes, but you know it is not so easily that you can swap the things, it is not so easy, things can become slightly difficult. So, I will just show some examples of this and we will try to go to some other thing. So, basically I am supposed to find a volume of a prism. Basically I am having an given plane which is of the form z equal to fxy equal to 3 minus x minus y. Okay. And then if I have this, I am asking you to basically find the volume over a triangular region. And what is the triangular region? I am fixing the triangular region at x equal to 1, I am looking at the line this, and I am looking at the line y equal to x. So, this is the line y equal to x and this is the line x equal to 1, basically this is the point 1 0 0, and if I look at this expression, this would be a plane which would be of this form. It will come down here and meet. Basically, then I have to find the volume under this. Of course, here I have to be slightly more, maybe the plane won't meet like this, plane would be slightly more sharper. So, basically now I am telling you to find this volume. So, this is a prism now. So, I am now trying to here you have to be very careful, because when x is varying from 0 to 1, y is varying from 0 to x, because on this line, because y can now vary from here to here as I draw the line, as x varies from 0 to, if x is at certain point x, then y, when x is varying from 0 to x, y is varying from, because if this point is say x some x, at that point y is equal to x. So, if x is varying from 0 to 1, y is varying from 0 to x. For any x that I take, y can take values from 0 to x. So, that is the key idea. So, any x that I choose here, y can be anywhere here. So, I have to swap off this part of the domain also. So, basically now my integral would look like 0 to x. So, these are my x functions, and here this is x is from 0 to 1. So, here I will have 3 minus x minus y, and we shall first integrate over y and then I will integrate over x, and if you finally calculate in the same way, this is 0 to 1, this will become, if you do it, so 3y minus xy minus y square by 2, here you put 0 and x. So, when you put 0, everything will be 0. So, this will become 0 to 1 3x minus x square minus x square by 2 that dx. So, 0 to 1 3x minus 3x square by 2, and if you calculate out, the answer turns out to be 1. I am giving this example from Thomas and Finney just for your illustration, the book by Thomas's Calculus, for illustration. Now, you also have to understand that there are certain cases you can, in this case you can revert back, because you see when if I now vary, if I reverse the region of integration, and if I say that okay, now if I look at this triangular area, so how did we get the region of integration? So, the region of integration is obtained in this way, that when you are at any point x, y can be anywhere here, y can be between 0 to x. Now, if I am now varying, I can do a different sort of variation. The variation can be of this form. That okay, I actually am varying along this line y from, because this is the line y equal to x, I am varying y from 0 to 1. This is the domain, but I am varying y from 0 to 1. As I vary y from 0 to 1, at this point y is equal to x. So, x can vary from y equal to x to x equal to 1. So, basically if I want to use x instead of, first integrate with x and then integrate with respect to y. So, when I have a particular value of y, then x is varying from y to 1, and then I can do this calculation in this following way, and then x is of y is of course varying from 0 to 1, and you would compute out and you would have the same answer. But this might not be always the case. You can, for example, find, so here you have to understand that things may not be always very simple, because for example, if you want to integrate this function, but just you have to do it over the same region. Now, first I do it over keeping x fixed at 0 1 and varying y from y equal to 0 to x. So, if I do that, then I am first integrating with respect to y, then I am integrating with respect to x. If I am doing this, then what I am getting here? So, I am finally getting y sin x by x, and from y equal to 0 to y equal to x. So, once you do this, so once you integrate, you have integrated this part, because now your x is held fixed, and you are just integrating it with respect to y. So, you just have y and then you integrate between the limits. So, 0 to 1, and this when you put y equal to 0, it will become 0, and y equal to x will become x. So, it will become sin x dx. So, the answer is minus cos x 0 to 1. So, essentially it is minus cos 1 plus 1. So, it will be, the answer it will be around 0.46 approximately. Now, you cannot do the reverse part, when you cannot say that can I do it with a different sort of thing, then basically then you have to compute it as follows: 0 to 1, y is been kept fixed, and then just as before, you know that x can move from y to 1, and then you write that this is sin x by x dx, and then so the then you have to essentially do this. The problem is that you cannot calculate this and get this answer, because this sin x by x does not have an antiderivative. So, every time that you will be able to get this form back is not always true. So, for that you essentially need an antiderivative of the function, but what Fubini's theorem says that it is continuous in the given region. We have to really figure out whether this function is a continuous in the given region. Actually, the problem would be coming at 0. So, you cannot really say that, because y can take the value 0 also. So, in whether it is continuous, and then x can take the value from 0 to 1. So, basically because of that, because of non continuity, you are being unable to handle this situation, while here you are lucky because you are first doing it with respect to y. So, this is one of the cases where things can just go bad. So, with this we stop here, and the next thing we will essentially give a very brief idea of what is a volume integral, and then we would immediately go over to what are vector fields and other issues. So, we can end our discussion with a very important result called Gauss divergence theorem, because Gauss divergence theorem is central to many things. For example, those who are from physics and electrical engineering, Gauss divergence theorem is fundamental to their existence. So, let us end it here, and we will come back to the next class very soon. Thank you very much.